Okay, so the purpose of this video is to teach integration by parts. And integration by parts really is our next major technique to integrate. U substitution should be sort of our bread and butter, right? We use that as often as possible. But if that doesn't work, and you're not recognizing is some special, completing the square or arctan, arcsine, identity like that, then integration by parts is what you want to try to do. And integration by parts, it's sort of like you've got a function, but someone else's derivative. It like if I look at one of the examples here, e to the x times x, right? Like there's like I can let either one of these be a function as a u, but the derivative isn't there. It's somewhat like maybe they represent someone else's derivative. And the reason that wouldn't be a chain rule, wouldn't be a u substitution, is because we never had the chain rule, right? A chain rule as a derivative is why you need a u substitution. You'd have a u that's embedded in a function, and then there's its derivative sitting out there. So that technique, the u substitution, that's a technique that undoes chain rule. But what if you never had a chain rule to start with? And so we need another technique. And the rule that we're going to be undoing is a product rule. And so when you have a function but someone else's derivative, that's kind of when you realize, oh, I need to use integration by parts. And it's pretty easy to prove. So just start with a product rule. So suppose I've got two functions. Function f of x I'm going to call u, and g of x I'll call v. So if I were to do the derivative of u times v, so another way I could represent this is u times v as a derivative. Well, you'd have to do the product rule. So we could do the derivative of u. What I think I might do is I'll say the derivative of u and leave v alone, plus the derivative of v and leave u alone. And so at some point we have to pick a u or pick a v. And so usually what we'll do is we'll just leave this u dv and subtract the v du on the other side. So now I've got u times v as a derivative minus, I'll put the v first, du equals the u dv. So in other words, I'm just subtracting this term. And then I'm going to introduce the integral. So introduce the integral to both sides. So integrate that and integrate that. And so what do we get? Well, the integral of the antiderivative or the derivative cancels. We get u v minus the integral of v du is equal to the integral of u dv. And that's really it. And so this is what you would be presented. So that's your given, right? And think about what this says. You're given a function u, yet you're also given someone else's derivative. And if you can identify both of those, then that expression is equal to this. And if you pick the right u and v, even though from a syntactical point of view, even though this says integral of v du, if it truly was coming from a product rule, you'll be able to integrate that. So again, that's it. That's our formula. We've got to know for integration by parts. And some textbooks refer to this as like a u-v substitution because you're looking for a u and a v, but the integral of u dv is equal to u v minus the integral of v du. Again, you have to identify, pun intended, you have to identify what's the u and what's the dv. So this is always the problem that you'd be given. And then if you choose appropriately, here's how you would be able to solve it. uv minus the integral of v du. So I'll show you. And I think we probably, if I remember right, say we start with that first example. So eventually you get used to, or you see different techniques and strategies, but a lot of times a good suggestion is to let your u be the thing that breaks down the quickest. And you'll know if you pick something wrong because the equivalency you got was actually more complicated. And again, you'll see what I mean in a second here. So I'm gonna say, okay, well maybe I'm gonna let u be x, I'm gonna let dv be e to the x dx. And it's a 50-50 shot. I could have also then, just to contrast that, I could have said, well, what if I let u be e to the x, and then dv is equal to x dx, right? That's my choices. I've got two things. I've got the x, or an x dx, and e to the x, or e to the x dx. So we can look at both ways and see why is one better than the other. So if I did choose u to be x and dv to be e to the x, then I've got to think, okay, well, if I'm choosing u to be x, its derivative is just 1 dx. And going backwards, if dv truly were this, going back that direction, that meant if my original v would have been e to the x, because that gives me that derivative. So if that is correct, then I should be able to solve the problem uv minus the integral of v du. And so u times v, so just identify what you'd picked. So x times e to the x minus the integral of v, which is now e to the x, du. Oh, that's great. Yes, I can integrate e to the x dx. It's just itself, right? E to the x minus e to the x, don't forget, plus c. And we'll check it in a minute. But let's say you went the other path. You had a 50-50 shot. So if you did choose u to be e to the x, then its derivative is e to the x dx. And if you did choose v to be x, it would have come from 1/2 x squared, right? Derivative. Remember, this direction you're taking derivatives, this direction you're taking antiderivatives, right? You start with the u, take a derivative. Start with the derivative already done, go backwards. So if we thought that was the right way, then we would have been able to solve uv minus integral of v du. Well, u times v is 1/2 x squared e to the x minus the integral of v 1/2 x squared du, e to the x dx. Now, look what happened. This is more complicated than what you started with. So it's another indication that you went the wrong way. It shouldn't be more complicated to integrate it. This is a strategy to help us solve it. And then, taking derivatives is so much easier than taking antiderivatives. We could check our work, right? So let's say we think that's the answer. Okay, so take the derivative. So the derivative of this is 1, because we got to follow the product rule. So that's e to the x plus leave the x, and then derivative of e to the x is itself, minus e to the x, its own derivative, plus 0. That cancels with that, and you're left with x e to the x, which is exactly what we started with. Okay, so again, a good rule of thumb, my takeaway, choose a u that might break down, because if you choose a u, its derivative right there, right, becomes, dx. Now, does that always work? Not necessarily. Here I know u squared, x squared could break down. But here's the thing. If I let my dv be ln x, right, let's say dv was ln x dx, and I had to go backwards, that relies on me integrating ln x. I can't do that, right? So when you see ln x, that usually makes it a good u. It's easy to take its derivative. We haven't learned yet how to do this. Spoiler alert, we're going to get there soon. So let's assign u to be ln x, and that's another kind of like a common thing. And when you see ln x, often that's your u, which means dv is equal to x squared dx, right? You have to name everything. So if this is my u, then what's left over, those two pieces together, form my dv. So u equals ln x, du is 1/x dx. Now, if dv was x squared, then if you go the reverse direction, going back, undoing that derivative, it would have been 1/3 x cubed. And obviously we put a plus c, but we'll just take care of that constant at the very, very end of our problem. So if we chose correctly, we should be able to solve uv minus the integral of v du. Right? If I can do that correctly, then I chose the right pairings. So what was u? U was ln x, and what is v? 1/3 x cubed. Not a big fan of that order, so I might switch it. Minus the integral of v, 1/3 x cubed, du, 1/x dx. And because of the way this worked out, 1/x times x cubed, absolutely I can integrate that. And so I'm going to rearrange this. I'm going to put this in front. So 1/3 x cubed ln x minus, and then if I simplify that, that's 1/3 x squared dx. And so that's just a power rule. So then I still have my 1/3 x cubed ln x minus 1/3 x to the third divided by 3 plus c. And then we can just go ahead and clean that up. 1/3 x cubed ln x minus 1/9 x cubed plus our c value. And, again, it might be worth your while to take its derivative because we could check our work. So much easier to take a derivative than an antiderivative. So then that would be a product rule. Oops, I think I'm out of space there. So the product, so the derivative of 1/3 x cubed. So the 3 comes down. If I use the product rule, that's just x squared. Oh, I didn't mean to get the chunky marker. X squared ln x plus, and then we leave 1/3 x cubed alone. The derivative of ln x is 1/x, and then minus 1/3 x squared. Derivative constant goes away. 1/3 x cubed divided by x is 1/3 x squared, which is there. And so we get x squared ln x. Now, I wasn't sure if I had this on my slide or not, but it doesn't look like it. But let's go ahead and just do one more. I think if I were writing this book, which I did, I would say, let's integrate ln x, right? Why not? And I just got done saying we don't know how to integrate ln x. And you're right, we don't. We're going to use integration by parts. And you might say, how can you do that? Mr. Brown, we just have one thing. Well, we have one thing that's like a function. We also have an understood 1 sitting in front of it. So I'm going to let u be my ln x, and I'm just going to let dv be 1 dx. All right, and we'll see what's going to happen. So we take our derivative. So du, I'm so excited here, equals 1/x dx. And then if v is just 1, v would have been x. So watch how this works. Again, going down, you take derivatives. Going up, you take antiderivatives. And I think this is example 3. So if I did this correctly, uv minus integral of v du. Well, u times v, so x ln x minus the integral of v du. 1/x dx. Again, there's your v, there's your du. And that is something we can integrate. So I get x ln x minus the integral of just 1 dx, which is just x. So x ln x minus x plus c. So that's the antiderivative of ln x. And check it out, right? Do its derivative. Product rule. So derivative of x is 1. Leave ln x alone. Plus leave x alone. Derivative of ln x is 1/x. And then derivative of x is 1. Constant goes away. This is 1 minus 1. So it's ln of x. So awesome. And some students decide to memorize this antiderivative, right? If it comes up so often, the antiderivative of ln x, like if you see that, some students just say, hey, I know it's x ln x minus x plus c. I suppose it's up to you if you wanted to memorize that. I don't think you have to. You could just use integration by parts to show, oh, here it is, and there's your antiderivative. Okay, so I'm hoping that makes sense going through these. And again, big focus here is just that this undoes product rule, right? It's a technique to undo a product rule, and we'll add that sort of to our arsenal of techniques when U substitution doesn't work, and when we realize it's not a complete the square inverse trig kind of example.